All right, well, thank you for coming. In case you guys don't know yet, I am Tom Pittenger. I work at Intel, and no, I'm not going to tell you how the lecture works. I get a lot of requests about auto landing or planes. Lots of people just do it horribly wrong, and look at lots of logs, and it just drives me nuts. So I thought, well, I'll talk about it a bit. Mainly there's a whole lot of documentation about this on the wiki. So things that we talk about at length on the wiki, I'm going to skip over a little bit and refer you to it. I'm going to try to talk a little bit that's easier said in person than text. So basically, figure out your aircraft, figure all that out. What kind of hardware is good for auto landing, the stages of it, as well as how to set your missions up, because that seems like the hardest part. Everyone just gets all those wrong. All right, so basically, know your aircraft. The critical thing is know how slow you can go. The whole thing about auto landing is you basically want to go as slow as possible when you touch the ground. But stalling is bad because then you crash and all that. So you want to be above the stall speed, but as slow as possible. That's gives you the gentlest landing, essentially. So figure that out, as well as auto-tune your aircraft. So with not a lot of stock aircraft, a lot of people just download it, fly it, and that's it for years. So it's always best to at least auto-tune it, learn about the characteristics of the aircraft. There's a text controller, which is the total energy control system, which I'll talk about a little bit. And the glide slope, which is what this diagram is about. So that's just basically how efficient your aircraft is. So with no energy, how much, for a given distance, how much do you drop? So that's basically your glide. The text controller. This is basically kind of always figuring out this big mixture of, if you put energy into it, then you keep going. So if you take energy out of it, you're going to drop. So there's always this balance to it. So more speed, you pitch up, and vice versa. So this during flight, it's not a big deal because usually you're keeping your same altitude. So it's fix your altitude and then kind of add throttle for a little bit. But on landing, all that's kind of adjusting. So you want to tune this a bit to figure that out well. There's a lot of text about this on the wiki, so there's a full page about that. And if we need to add more questions from you, then we can just add more if needed. There's also 26 or so different parameters on that. So I'll talk about it a little bit. So determine your glide slope. This is one thing that most people just don't know about or don't do. So ultimately what you want to know is, if you don't put any energy in the system, how well can I fly? So ideally you just turn your motor off and you glide right into your landing. That's essentially the best case scenario in a perfect environment. So when tuning, it's always best to have a quiet environment, so no wind, as little as possible. It always skews things. You can always fly later with wind, but when calibrating and tuning your aircraft, as little wind as possible. So the method is fly-by-wire A, and then this was assumed we've already done on auto-tune. So doing auto-tune is you figure out the PIDs on the roll and that sort of thing. So fly-by-wire A is it'll keep you flying around, but the A means the throttle is controlled by the joystick essentially. So you can actually kind of cut the throttle. As long as your throttle min is set to 0, you can kind of turn it off. And then you can basically try to level it off, and then it'll just kind of it'll keep it going, but you'll lose altitude. So the idea is try to lose some altitude and keep your airspeed going, and then see how much you're going to drop, and that ends up being your glide slope. It's just a height over distance. Ends up being pretty straightforward, just the arctan of that. That comes into landing to tell you what your absolute minimum, or maximum, I should say, glide slope is. So a lot of people just choose 10 degrees or 15 degrees. They have no idea what it is. The more efficient your aircraft is, that means with no throttle, how far you can go without dropping much altitude, then that means you don't burn off any energy. So that means you have a really shallow slope. So then landing being inefficient is actually kind of useful. So hardware. So for best case scenario, you have an airspeed sensor. that you doing just throttle-based landings are not optimal. So you're always going to be better if you can know the exact feedback of your airspeed. That's going to apply when you're actually changing your airspeed as you're going down, trying to maximize or minimize your airspeed to be like the lowest you can get when you're done landing. If you don't have your airspeed, if it's an internal estimate that we're creating, it's not always as good as an actual sensor reading of your airspeed. Nice to haves are a rangefinder that really gives you, how close you're out to the ground, so it gives you accuracy when you're flaring and all that sort of stuff. It also corrects for barometric pressure changes over time during your flight. So sometimes it's perfect landing, but if your barometer just drifted a meter or 5 or 10, then you're just going to kind of overshoot or undershoot. So the electronic speed controllers that can go backwards is nice, because if you're going too fast, then it's okay. You can manually slow down and just maintain pretty much any slope you want. So that makes it very easy to just do whatever you want for landing. Just say, allow your throttle to go negative, and just say, I want to go this speed, and it just makes it happen. And the fancy stuff would be flaps. There's 2 different speeds for it, and they're all maintained by airspeed. So with the parameters, you can say, I think it's flaps 1 or flap 2, but you said, if I ever reach this airspeed, then kick in 25% or whatever it is. And then if I ever reach this other lower airspeed, then kick in more flaps. So it ends up being a bit more drag but more lift. It's called concept of flaps. But then it allows you to actually fly at a lower airspeed that way. So
the LiDARs are useful out to 40 meters, but a sonar, mainstream sonars only get it work about 6 meters. Is that too late to help in the landing sequence, or is it?
Usually, I definitely recommend LiDAR. Yeah, sonars are good for flaring, because that's like a 2 meter sort of thing. LiDARs are obviously much better, far superior to rangefinders than the sonar. Yeah, LiDAR, even the cheap ones are like a 30 meter sort of thing, unless you have like tiny one when they're like older. So you want to do, LiDAR if you can. They're generally heavier and more powerful and that sort of stuff. We do have the ability to power down the LiDAR when you're above certain altitudes or when you're not landing, so that's a helpful feature. I've seen problems with LiDAR where it would actually jam your GPS or other noise issues. So when I fly, there's a pin you can use to actually power down your LiDAR. So I've been flying a lot with the LiDAR Lite V3, which we've kind of worked out the bugs on the software side to tolerate. I use it with the analog input. I don't use it with the HOC. But also there's a couple of Lightware, there's other manufacturers that do that. I mentioned the BL Heli for the reverse thrust. That's what we have right now. The wiki kind of talks about BL Heli or BL Heli compatible ESCs. When I say compatible, it just means you can put the firmware onto it and then you can program to go backwards, essentially. And you just set your middle point, instead of your PWM being from 1,000 to 2,000, it's 1,000 to 2,000, but instead of being off being 1,000, your off is like the middle. And then the negatives there. So that's what's in there right now. I'm working on making it so there's another pin that would dictate the direction. So that's coming soon for additional ESC manufacturers. I was going to talk more about the spoiler. So the airspeed sensor looks like this. This is pretty common. If you guys haven't seen this yet, you should look at one. I'm sure everybody here kind of knows about it, but watch us later on the video. They're a little bit finicky to get right on your aircraft because you want them in the front where you have clean air coming in. A lot of people put them towards the back or whatever, that's all we want. It has to be clean air, no propellers in front of it, so we're near it.
Just as a quick safety note on those, that sensor is very light sensitive. So a direct sunlight on the sensor can give you 35 meters a second indicators.
Yep. Yeah.
And it is angle dependent, so you can bank in flight and all of a sudden you have massive airspeed reading and come back and lose it.
Yep, so they're light sensitive, cover those up. Along with the pressure sensors we have, all the barometers, all those, the family of sensors is light sensitive. So this one doesn't get much attention, but I wanted to at least mention it here. So using a do-set servo, you can set spoilers on your aircraft. So I've seen at least one that has the Hobby King has this little spoiler kit you can get, which is this picture here. But that is on the left.
Yeah.
Right, it's a big one. So there's two modes here. So you have like a minor spoiler versus a major. Not sure what the terminology is, but during flight you can just slow down, basically induce more drag, and you can give it a little bit. So you see up here where you're high, your altitude's high, and you're just kind of spoiling off a little bit, and that just kind of gives you a way to decelerate without losing altitude. And then on the bottom is a picture of full flaps, full air brakes, just slamming the brakes using air as your mechanism. So on the left, the pictures of Bobby King is a little servo that's when you set it full, it kind of comes out and does this. So it's like a big bar that kind of whoop, like this, and then you can put those in different ways. You can put them in line with your frame, so it kind of this thing that kind of just grabs the air, or you can put it horizontal where it's just you break a wall in the air. And if you want to slow down, that's the way to do it. Without slamming the brakes. You can fall in the sky, but a lot of times for heavier aircraft, you would land and then you just kind of keep going on the wheels. This really gives you the ability to slow down a bit. I didn't know where to put the slide, but before I talk about the next stuff, I can answer this. There's parameters. There's lots of them. There's over 1,000 for playing. And this is where to get to them all. A lot of people go through the wikis and the wizard, and they say, "Oh, it's up for auto landing," and all they see is the standard parameters. In Mission Planner, there's you go to config and then planner, and then there's advanced options, and it's labels change a few times. But anyways, put it into advanced mode, and then the full parameter list comes up, and then now you get this giant thing. On the right side, you can search, and you can type in land or land underscore. It'll pull all the land related things, or text, or all that. So when we're referring to a lot of parameters on the wiki, we'll say, "Oh, it's parameters." People just don't know how to set parameters sometimes. Okay, next stage is the flight stages. So this kind of describes when you're landing, what the flow of it is. So the main point that a lot of people miss is it's the mission. Most missions are just like 2 points. That's the scope of landing is just 2 points. So it's the point hop high and the point on the ground. So typically your landing point would be like 0 altitude, and then some of the navigation point could be a loader, it could be a waypoint, whatever, up high. And then once you're actually executing the land point, that's when all these land parameters come into play. Anything before that, they're not. You're in some normal mode. So we call it, take off, you fly around in normal, and then once you start executing the land mission item, this is all during auto, you start the approach. So the approach could be whatever length it is, and then we have a pre-flare, so there's some parameters that will set up the pre-flare, which is before the flare. And then that's just another threshold that you can optionally set a lower airspeed at, like just before. So you can kind of set it before you're in like a safe airspeed. You have a cruise airspeed, and then you have like an approach airspeed, which kind of slows down a bit, and then a pre-flare, you slow down more, and a flare, you're just hitting the ground. So at a flare, motor's off, you're still armed, but you're essentially disarmed. The motor's been cut off, and you're just basically gliding until you hit the ground. So what a good one looks like is like this, where you would approach the navigation point that you're starting from, that you start going down at, is not spoon-fed down to that point. You're up high, and it's landing the whole time. So that's going to be up at 30-something meters, and so you're actually it's trying to compensate with lower airspeeds. It's trying to track these during that process. So typically you'll kind of always overshoot as you go down, because instantly it says, "Oh, you're going to go down, but you're not there yet," because you kind of chase it, and then so it levels out. So it takes a few meters of you actually elevating to sort of tracking the slope. Before you start during the normal part up top, the airspeed is the trim airspeed CM. So that is your cruise speed for your missions and whatnot. So that's going to be 15 meters, 16 meters per second, something like that. When you start your landing, then you have this text land airspeed, and that is, if you don't have it set, it just uses the other one. But if you set it, then you can set it as a lower speed. That it's essentially the same thing, but it's during this approach part, you can have this lower speed So it's trying to reduce the speed while also going down. So it gives it some time to stabilize, which is why it's hunting a little bit. It's trying to balance that. And then you have this point where you flare. So the flaring is, there's a flare and a pre-flare. The pre-flare is triggered, it's an OR statement. So you can either trigger on altitude or trigger on, with the current velocity, how many seconds before you hit the ground. So that's the land PF alt or land PF sec. It's an OR. If you set them to 0, then it gets ignored. It only uses the other one. So typically, if you want to mix it both just for like a safe thing, one just higher or some of for useful value, up to you for your tuning. But that's some other high, maybe the pre-flare I use something like 10, 12 meters, and then at that point it starts using the control. So the text controller starts using the land PF airspeed. So now it says I went from a relatively high airspeed for my cruising from all of my pictures at the trim airspeed. And then I've slowed down, during my approach. I've tried to maintain the land airspeed, and now I've pre-flared to even a lower speed, and then at some point I flare at a flare alt or flare sec. At that trigger point, I'm off, and I'm just trying to just bleed off until I stall or touch the ground as slow as possible. So it gives us ability, this margin of error of you can slow down, but you're still safe in this. Up high, you're at a conservative airspeed, and get down, you can get a little risky as you're slowing down to the ground. So this is a good one, a good chart where your actual is meeting your theoretical. They compensate, they get sloppy, and then they go, and then your airspeed steps down. Oh, you went too fast, and you kind of slow down. So there has to be a little bit of gap, several seconds or so between the stages, so they can compensate, or so they can catch up to that. This would be what a bad one looks like on the log. So you say, oh, I'm going to go the slope, and then your airspeed, and you're just not able to track that. You're either going too fast, or it's too steep, where your aircraft just, your glide, this is an example of your glide slope being too steep versus what your aircraft can achieve. So this is what logs will look like. I don't have any actual logs to show of that particular one, but here is kind of a typical looking log where, I don't think I'm pre-flare on this one, this is just a regular flare, but you see from the top left going down is your altitude. So you kind of level off and it drops down, the demanded height kind of steps down and says, oh, you're going down now. And then your altitude always overshoots and you kind of catch up to it. And then your airspeed would just dip down to that point until you hit the ground. And then for reverse thrust, which is your demand would just drop down and you're terribly overshooting and just slam on the reverse for the thrust to really get down there. So at first you kind of speed up a little bit as it tips down, and then you're throttling up or throttling negative, and then it kind of catches up, and then it's kind of hunting to get your airspeed down low, but it gets down much lower that way. And then you see the second jump, where it's right here, where it's hitting the pre-flare. So the secret to this is practice, practice, practice. You have to do it kind of over and over. And what you want to do is get your altitude error as low as possible. That is the difference between the desired versus the actual. And the secret is if you can get that near 0, it's hard to get it actually 0, but it'll kind of hunt to be low. Get that at the point that you're doing the flare, or at the point that you're doing the pre-flare. Because if you can repeatedly do that in all wind conditions, then you'll have a very reliable landing every time. You can, so in Mission Planner, you can double-click on the lower left here of the boxes, or in the the real-time log stuff. But you can double-click on here, pull up Alt Error, and it shows real-time. Same with the airspeed. And also there's the landing abort. So this is a good repeat pattern where you're coming in for a landing, and then you hit your pre-flare, which is 10 meters or so, and you will see how well did I hit that point. And then you can just abort from there. You'll circle around, and then you can repeat that and tweak a parameter, and then try it again, and not actually land. Just kind of repeat this process. It's much faster that way.
So what mode happens when you click abort landing? What is it?
So the way abort landing works is, I'm talking next 2 slides away. So the abort landing is, you can trigger it 2 different ways. There's the, it stays in auto mode, and there's 3 different options. 2 of them are actually the most popular. I'll talk about the 2 major ones. The way you trigger it is either the throttle on your joystick, on the transmitter. So as long as this parameter is set, so the land abort throttle, I think the default's 0, so if you have to set it to 1, that allows you that if you were to throttle up above 90% or so, if you throttle up and just trigger it, it doesn't just stay up, just trigger it and it will trigger abort. What it'll do is it will repeat the takeoff that you did, the auto takeoff. If you've never triggered it, or if you didn't perform a takeoff yet, then it'll have a few conservative options you can do, or conservative slope and whatnot, or pitch, I should say. But it will just take off and then reach whatever your takeoff is, or 30 meters, I think. It'll basically just hold that heading and just take off, and then it will jump to either the last point you started at, the top of your slope, or it'll go to do land start, which I'll show you in a second. So if you triggered either the button here or the joystick, and then you get either of those 2 behaviors, is the waypoint or do land start.
There isn't land abort dead, the automatic abort for slope tolerance.
Yes, so there's another way that it'll self-abort. So that's land abort deg. That's a different degree. That is, if it is coming in too high, and the barometer says, "Oh, you've drifted 10 meters on your barometer during your flight," and we don't realize that until it's kind of too late. And to correct the slope, we have to go really steep to actually land everything. If you are if it's too steep, depending on what that barometer is set to, then you can say, well, just abort, remember what that offset was, fly back around, and then now you're actually coming in with that compensation already applied. And then you should come in at a perfect barometer offset already applied when you come in. So it'll automatically do all that for you with no hands if your barometer is drifted a lot. Which happens on hour-long mapping missions and all that. It's very common to drift 5+ meters. And when you're trying to land and you're 5 meters off, it can get ugly. So that requires a LiDAR, some sort of correction to tell you that you're off that much. Mission types. So, yeah, normal, which is the common one, reverse thrust, which I mentioned a little bit, the spiral, deep stall, and parachute, which I won't talk about, but it's kind of the punt option, where you just throw a parachute like, landed! That's pretty much all there is to it. There's like different ways of packing all that, but you can just do that. And also, magically, we scripted this, so we can do more complicated things. We want to detect wind automatically, whatever modes, and so that'll get much more complicated soon in a scripted manner that you can just download and say, oh, just detect the wind and always land this way, and oh, or this way, and just kind of magically does it for you. So all these things are coming soon as scripting comes online. So the normal glide slope method is the one that most people that always use this. And first, take off, and then it just does a bunch of waypoints. That's your mission. So top left would be just point, whatever your mapping thing is or whatever you're doing. And then you'll notice as a do land start, so do land start is useful. Well, I'll get back to that. Do land start is a marker for the end of the mission, or for the beginning of your start. So after that, it just moves on to the next line, and the next line could be a waypoint or loiter waypoint. Loiter all. The idea of having a waypoint that's up high is you can actually come to that point and then loiter down, instead of coming down to that point. Depending on how you came to this point as a marker of the mission. And then, but the key part here is you just have a point high and a point low and a slope. Now, it won't actually do the landing unless you're actually lined up. So if you're hitting that top waypoint, which is point 10 in this case, so once you've reached 10, if you're 90 degrees to it, and you're still doing it long term, you're not going to start landing yet. Because landing, part of it is to restrict some of the bank angles and that kind of thing, more steady. So you're actually going to start turning real slow. So it's going to be hard to line up. So the best way to do it is to set a point before that you've reached, and then you line up. And so you actually, by the time you hit the waypoint, you're ready to go, and it just kind of tips down and starts your landing. If you're doing some maneuver as you're doing that, it's just going to be sloppy. And you're not going to actually have the glide slope that you're trying to achieve. So on the bottom right here, you'll see that there's next slide. Anyways, so between points 10 and 11, You can see here, for example, I have minus 10 degrees. So that's a common thing for lightweight phone planes. So just lower the number, the better. It's easier on the controller. Usually, if it's too shallow, you can actually give it throttle to maintain a speed. Once you hit that number too high, then turn the throttle off. If it's going down, just speed up, speed up, speed up. So that's what the whole glide slope test is for to do. So this is normal. This is what I recommend that most people do, is do a dual start and then just line yourself up before you start. And then just back off that point depending on, back up to 2 points at whatever altitude you want. The dual start is just a marker. It does not actually execute the mission, or nothing executes at that point. It does have a valid lat and long. And what that means is if you have multiple dual starts in your mission, whenever either an RTL or auto land happens, it will jump to the closest, wherever you are, it'll jump to the closest dual start in your mission. So you can have 10 different dual starts and have all the different land scenarios all over the place. So if you RTL and you're over here, took off over here, you can actually have a contingency plan to land the RTL and then switch back into auto at the dual start that's nearby. And then it'll do some sort of pre-planned landing at that point, or somewhere between, or back home, wherever you're at when it happens. So that is nice when you are doing an abort landing. You can just come back and restart. So this really helps when you have that kind of plateau up top of 2 points. You can come back to that far point and then turn around and get lined up. Because if you're starting your landing facing 180, that's not going to work very well. Reverse thrust, the missions for those, pretty much the same thing, they're just steep. So here it shows minus 30 degrees. So I was demonstrating this at CMAC, and I had a Skywalker X8 where we're doing 40 degrees with reverse thrust. So you can do pretty crazy things. Your slope becomes arbitrary, because if you just go too fast, you just go backwards faster. And it just compensates. It's all airspeed, so it's all airspeed triggered. So if it's just trying to find a certain airspeed. So if you're going too fast, it says speed down until you reach that airspeed. And it's just like it's just hunting to figure out your airspeed to match. Helical landing. So I did some testing with this. I don't know if anyone's actually doing this, but I was to show how I've done it. These reflect done with Skywalker X8s. So that is coming back, you just loiter down, and then when you come out of the turn, you want to be lined up with the runway. If you line up the points in the middle, then you're going to be kind of doing this weird turn thing as you're landing. So you don't want to do that. It's doing a tangent exit. So tangent exit is something relatively new. It's done like this. This is a map of showing a mission of what a tangent exit versus a regular exit looks like. So it's all about cross-tracking after you leave the point. So you'll see example point 3 here. You are exiting the mission on the tangent versus 4, you're cross-tracking back to the middle. And then can't see it here very well, but it's the points are I'll show the next slide, bigger next slide. But there's a flag in the loader to all, loader turns, loader anything. On the last of the 4 little parameters there, the number ones and zeros. The last one is tangent exit. So this is how you do that. I have 2 slides here. One that I showed how I set it up, and then one that actually flies. So this is the setup for it. Point 2 is just you take off. I'm just loitering at some point, and then now 3 is the setup. And on 3 we are going around the turn. Point 6 and 7 is 7. We're going to be removing soon. But it gives us a good marker of distance when we're calculating. We can go over here and say meters distance between it. So this is going to be you want to basically be loitering down over that point. So when you exit, you can achieve that. So also on the tangent exits, they don't exit until you are lined up to the next point. So it grabs the heading and says your heading must actually be aligned. Your ground heading, not your actual heading, because you're yawing the wind or crowding. So when you exit, you should just be lined up, and you should just go straight into the next point. So you don't want your radius to be different then. So if you have some huge radius and then your bottom is here, then you're actually still going to be tangent exit and then still the swerve in. So So what I do is I use another point that lines me up, and then when you actually do the mission, you just have it looks like this. This is what you're loaded into the plane. You just have the point that's off the side, and then it just magically exits on that side and lines up. But it doesn't look like that on the map, but that's what the behavior is when you exit the aircraft. And then deep stall, something we've added recently, and Michael Michael DB will be talking about that.
So, switch the video real quick. I just want to start out with a video of what this looks like and a disclaimer of we have the feature, but if your aircraft can't take the impact you're about to see here, this is totally irrelevant to you. So I just want to start out here. This is harsh on an aircraft.
Well, and also the wing is intentionally done for this.
Oh, no, don't tell them that.
Oh, okay, alright. Surprise.
Rapid disassembly is a feature.
On schedule. This is scheduled. So it's vertical landing.
So that will max out your accelerometers every time. I've yet to tell how hard we're actually hitting. I'm waiting for somebody to give me things that are more than 30 Gs to find out. So that's our peak impact there. So that is a deep stall landing. The prop was spinning there yourself. That's actually just windmilling, so there is no energy being put in there. The elevator is just locked up very high, and the aircraft is descending at a steep angle.
So this is slow. This is slowed down.
You're doing this on purpose, right?
Yeah, totally. I just happened to do it. Oh, that's great. But yeah, so the wing is disassembling off the aircraft and that's shedding energy because now the wing can just flex by itself without having to transfer that into the fuselage. From a design requirement, there isn't a strict reason you have to shed the wing like that. If you know if your aircraft can take it, then that's fine.
You see the wing actually kind of go down, which
Yeah,
washes it up.
Something that has like 11 degrees of polyhedral, that's a flat wing during the impact. And that's bending carbon fiber, spars, and stiffeners.
So important to note on this aircraft is no halo. Yeah, it's just hooked in and it just puts over the tail. So it's designed to pop off the.
And Michael,
Yeah.
how long after that kind of deep stall landing you can fly again with that plane?
It depends on what you're doing. Depending on your ground, for us, in excess of 200 minutes to airframe is quite common. So deep stall landing is actually, in a lot of ways, it's one of the more automated and most advanced landings we have on plane. Unlike everything else Tom was just talking about, deep stall landing is put a single waypoint and that's it. The aircraft will do everything for you. So when you plan this landing waypoint, you say, all right, I want you to land at this latitude, longitude. I want you to enter from this altitude. So instead of a normal landing waypoint where we say 0 meters is ground level, you say, like, I want to approach from 60 meters. So you put in 60 meters as your altitude. We fly to the waypoint, the aircraft will fly to the waypoint, which is step one. We will enter a loiter around it and descend to the appropriate altitude. So if we get to the waypoint and we aren't at the target altitude yet, we hang out until we're there. We'll then also ensure we do a complete 360 once to try and give the wind estimator a chance to catch up, because deep stall is highly dependent on the wind, which is why I'm the one who complains to Paul about, can we have resets? Can we have resets? For the record, a 1 meter second error on wind estimation from 60 meters will cause out to 9 meters of ground error. So for our impact location, we're very dependent on having a good quality estimate. So once we've done this loiter around the point and we know where we want to hit, we will compute what the optimal path is. For deep stall, you always want to be going into the wind. The reason you want to do this is if you're going with the wind, we have more energy when we hit the ground because we're moving faster. So by going into the wind, we're always going to have the slowest possible approach. And we also have a much more stable aircraft. It's hard to fight the wind sideways as you get pushed sideways. So auto deep stall will always go perfectly into the wind, regardless of whatever heading that requires. So here, in this example, with the wind 4 meters a second, the aircraft is going to approach at this heading. When we pick a tangential exit, much the same way that Tom was talking about, automatically, we generate that for you. So then we stay in the loiter until we're aligned with this, and we break out onto that entry.
Is that just the loiter radius that you're using for the size of the circle?
Yeah. And that's all controlled just by the aircraft's loiter radiuses.
Yeah, Michael?
Yep.
That's just a clearly defined point when it goes into the deep stall. We could do a VTOL back transition there because a lot of our VTOL airplanes, particularly sweeps and things, they hate being crosswind.
So there's actually a couple interesting ones. If you actually think through what I'm outlining here, this is actually giving you predictive entry for parachutes as well. We don't support it at the moment, but this is predictive entry based on the relative wind for a point. Now this is using active steering, the parachutes won't have that. But you could use this logic to say, I pop the parachute here, and with this wind, I should hit there.
Yeah.
but also the tail setters, the vector tail setters particularly
Yeah.
are very appropriate.
Might be cross when you transition.
You just overwrite the predicted spot to your landing distance and
So as we're doing this entry, so as we're doing the loiter till we've done the breakout, because the wind can shift on us, and for example on my aircraft, depending on heading, I'll see the wind shift by about meter-second velocity, and the heading will wobble a bit. So until we've selected something will allow the heading to drift. And then once we do this entry, this is where we're going to enter that flare. So as the aircraft comes in, you're flying along a normal flight, you do a flare, and that gets into the stall regime. So we'll update this depending on any changes of the wind to that point, so that you'll watch that line kind of drift back and forth on the map from a visualization perspective. But when the aircraft hits that, it'll flare, it'll enter the stall, and we'll do a couple stage transition where, depending on the indicated airspeed, we'll reduce or change the amount of control authority we'll have. Because as you do this high alpha and you'll enter a 45-degree angle here, you don't want to be putting in a lot of rudder, because you end up kind of tipping over, you can enter a spin. And then once we've entered a stable stall regime, we will actually cross-track and we'll fix being blown off course here towards hitting this point. So if the aircraft is being blown to the side, it'll turn back in and get back on the line. The end effect of this, though, is that anytime you have to turn, you're robbing yourself of forward velocity, which means you'll be short from the point. So a normal deep stall landing, you'll have very good lateral control because the aircraft will always turn and fix it. However, this does come at a cost of you'll be short or long, depending on how much correction you have to do. So with that, it's great landing for a lot of reasons if you can take the impact. So for us with no wind, which is one of the worst things to handle from a prediction perspective, because you just watch the angle change rapidly and it's not a very stable prediction. With no wind, we're looking at a slope of around 40 degrees to the ground. So that's where reverse thrust starts. Really good reverse thrust is 40 degrees. Our worst case is 40 degrees here. As we gain wind, we come to vertical, and we can actually do backwards deep stalls as well, depending on level of wind when that crosses your normal forward speed. So first time we went out, the plane is steering backwards. That was kind of cool to watch. It just kind of worked, which was great. So for deep stall, there's a couple of important parameters to tune. The main one is this is using vastly more elevator control than the autopilot's allowed in flight. So autopilot for us is using maybe 10 degrees or so of elevator travel normally. And we're going into deep stall, we're pulling that up to about 40 degrees. So we're actually manually overriding and specifying PWM value for now. And it's only allowed during this mode because it's just unstable and it's fast the outside, but the autopilot can fly. We gave the autopilot that little control, it just porpoise, the PIDs wouldn't handle it. So from a prediction perspective, especially if we want to move this into parachutes, there's two main things that come into play. When you enter a deep stall, there's this stage where you decelerate and get into a stall regime, and then there's a steady state once you're stalled out. So there's just a slope equation for how far you'll travel based on relative wind as you're doing the entry. And again, we've pulled all of our numbers for this from log analysis. So we just did this repeatedly and we just found averages and did a bunch of statistics. And then once you're doing the descent, there are two numbers. One is your forward speed, assuming no wind, and one is your downward speed. So for a parachute, these are what you bring in quite easily based on your parachute. I'll drift this far forward with my speed or not. Your forward speed on a parachute is probably 0, but depending on your shooting style, that's not the case. And then that'll take into account the wind, and also take into account any crosswind component that's developed here. So even if there is a crosswind by the time we get here, because we can't chase the line forever, so we'd enter being out of heading. So we'll take into account all of those components. But this is all just a statistics problem at this point. There's not a good tuning approach to this. Deep stalls can be avoided. It's quite easy. Put the elevator back down, the aircraft pitches down, gets a ton of airspeed very, very quickly, and it just works. You go right back into takeoff logic. So the same way you can abort any of the normal ones, you can abort deep stall landing. The main difference is deep stall has an additional parameter that says below this altitude, refuse to abort. Because first thing you do is you go full throttle and go straight down. You don't want to be doing that at 5 meters because that's one of the worst things you could be doing.
That's deep parking.
Something.
Underground.
Rapid determination. The other things that if your aircraft is capable of doing deep stall landing, this has been hooked into from an autopilot side. So this is actually connected to AFS. So you can terminate your aircraft with deep stall at any time. So you can actually use this from GCS to say, terminate my aircraft. This is useful from a safety perspective because this is far lower energy than spinning the aircraft into the ground. It's much easier to say, just enter deep stall, it's a stable regime. We know what our maximum energy is when we hit the ground. We'll try and steer. So this is actually hooked to the AFS library if you want to use it that way. But AFS is pretty weird for most people. Again, this is outside of most aircraft's capabilities.
Scripting.
Yeah, so I mean, a lot of the approach stuff, if scripting was around, probably would have been done all as a script rather than putting this into ArduPilot code, because this is a very specific use case. You have to have an airframe that can do it.
This would actually probably best removed, actually, if done as a script. To do scripting.
Potentially, we might end up, if we want this into parachute stuff, either into common library or look at just saying some of this days as helpers.
If this ended up in parachute, deep stall, and VTOL landing, then it's probably worth keeping it in there. But
Yeah, as is, it's I will freely admit it's very specific.
Have the helper functions in C++, but then the control logic is a script.
Yeah.
But all of the maths as helper functions.
So the only other one I really want to note is that deep stall does not support terrain altitude right now. It will handle absolute altitude locations or relative. So if you are doing an absolute altitude one, your altitude field is the ground elevation you want to hit, and your abort altitude field on a waypoint entry for landing is actually your approach altitude. Because there aren't 3 fields in a deep stall or a landing waypoint. So planning a deep stall is also trivial. This is, if that was just takeoff and some waypoints, doesn't really matter. A deep stall is just a land waypoint. There is nothing else to it. For normal safety reasons, with planning do land starts, you can jump to it nicely and it makes aborts and restarts really well. Because if, for the record, for a plane, if you abort a plane landing, you don't have a do land start, plane goes back to the previous waypoint automatically. So on deep stall, if I finish my survey grid and that's a kilometer away, I don't want to go back to my previous point and refly that whole approach, I just want to do the landing. So for deep stall, I'll just always plan to do land start, and that'll work out just fine. And I think that's all I have on deep stall. So.
Thanks, Michael. It's important to note on here that normally your land altitude is 0-ish or so, altitude where you take off from, but on here the altitude, the example here is 60, which was specific because you might.
Because that's the altitude we like for clearing trees, and it gives us time to see it stable and doable.
So that's where you actually trigger the.
Yeah, that's the whole approach.
script
altitude.
start, yeah.
In terms of triggering an elevated PWM, does that happen automatically or?
Yeah, it's all done by outside.
Yeah, there's 10 or so plus parameters there. Land underscore DS underscore star. There's 15 or 10 different parameters that tweaks it, something like that. And I think that's it. Any more questions?
So just a final question about the deep stall. How do the electronics, like cameras and things, handle that sort of impact?
Well, you can eject a camera from the plane.
Deliberately.
So it's
not really. They handle it surprisingly well. So inside that plane, for example, everything's mounted basically in foam. So we haven't had any problems with wear or anything like that. Camera might come out, or we might pop SD card out of a slot, again, in the camera. But from a reliability perspective, everything's been fine.
But then again, if the whole plane is designed for a deep stall, probably you will also take care of the cameras and all the other.
Yeah, again, this is very specific of, once you move to an airframe that can do this, this all becomes a concern.
Correct, yeah.
Yeah. You're not putting a DLSR with an expensive lens sticking half an inch out the bottom of the aircraft.
We are using like Sony A6000 and A7R with $700 lenses, so they are relatively expensive.
Better close the lenses before landing.
How dare you treat a camera out there?
Well, Daryl's crying.
I should tell you what else people have asked to put
Please,
in.
think of the children.
Yeah.
He hasn't started testing.
Yes.
Someone's asked about phase 1.
So,
Everyone wants to pay for that, though.
This is actually a really good video that will end up on YouTube so people learn how to land their airplanes without crashing them.
Yeah.
Without crashing.
This one? Or
That's more.
Yeah, let's have one more time.
this is something to crash in, I think.
Yeah.
No, that's
And
intentional.
I mean, like, your presentation as a whole is going to be really useful for users.
Yeah, there's also on the landing.
Yeah, I
Alright,
know.
landing.
I could see what he was doing. It was very clear.
If you scroll down, somewhere at the bottom is a video of me doing this with the Skywalker X8. So this is a 15 degree, I think, which is not too impressive, but it's a 15. It comes in and does a relatively good landing on grass, which normally the Skywalkers are notorious for real long landings, so they kind of hover there, and since their wings are so low with the delta wing, or with the wing body, it just gets you a lot of ground effect. So you kind of, as you get down close, you kind of just hover there for a while. Which is one of the reasons why I added a parameter called land, or text land SRC, which is the sync rate change, yeah. So that's, if you pass land, it will push you down a little more, and it's proportional to your distance. So as the farther you are beyond the land point, it just pushes you harder and harder and harder down. So you will guaranteed to be driving to the ground. So the higher the gain there is, the faster it pushes you down. And I think it's proportional to like per meter or something like that. It's a velocity per meter kind of ratio. That's some of the doctors.
So the point of deep stall is we don't have long runway, right? Just
Right,
video
yeah.
was done in a very large open area, so I assume that wasn't.
Yeah, like for Michael, it's a hand launch and then whereas land and spot kind of thing. So you don't need.
So when we're an airplane that flies for 3 hours, our glide slope for landings are insane. I've tried to do a normal plane landing and I needed more than 800 meters and I was still over speed at the end. So at a certain point, it doesn't work out anymore. If we had enough spoilers and extra surfaces, then sure, but we don't really want to carry them around.
Yeah, for a very efficient aircraft like that, we have a really nice shallow glide slope. It's really good for efficiency for long flights. Then it's hard to bleed off that speed when you're actually on land. So this is where they went.
Yeah, those spoiler things from Hobby. That's
But that's the idea. But again, like for 3 hours, he's lugging around, so it's more weight. There's always that trade-off.
that increases stall speed.
You could crow brake with the ailerons up and flat.
Yeah. So I don't know what the status is of that, but yeah, there's braking of your spoilers or of your ailerons. So I think it's differential spoilers, differential spoilers, or I can't remember what it's called. Anyways, yeah. So if you have like two ailerons, like flap and aileron, you can actually go separate on them for crowing. There's also a technique that I don't think we support, but you could do ailerons up and then your elevator down, so you kind of bleed them off there. Yep.
You know anyone that's doing reverse thrust of the tractor or motor front configuration?
No. So I've intentionally avoided that because I always think it's a bad idea to put the motor. Reverse thrust would be in the back because the idea is that it tries to yanks the motor out. But but on the front, I think just usually it's for folding props and such. But I don't know if anyone's doing that. I'd love to hear experience.
I have tried that, and you break lots of props
Yeah.
doing that.
Well, do you break it because they're spinning when it's ground?
Yeah,
Okay.
kind of that.
Well, they're supposed to stop spinning.
While you're landing
They
here,
are, but when you are doing, I think, with the wind or something, they are not able to judge the height, and it kind of the flare has not been activated, and the spin continues, and like the prop breaks.
Well, that's a problem on any kind of aircraft. If you're still actively powering the motor as you're at the ground, potential's high to break props.
Yeah, and even sometimes like when the prop stops and it's like facing like this, the prop is like vertical and it will like catch into like the ground or something like.
Right. So on my particular Skywalker X8, the props are folding. So they even windmill a little bit when they hit the ground, but they would just fold up so they don't damage. So.
And I just want to also point out what Tom and Michael have done as far as the structure of ArduPilot with landing, because landing in fixed wing was just all built into the mainline vehicle code, and they spent a lot of time splitting it out, modularizing it really well, so that we can now plug in other landing strategies. We've got a whole lot they've presented here. We've now got the infrastructure, so when another person comes up with another even crazier landing strategy, it can fit in there as a new type of landing back end and be code that is maintainable. So I just wanted to say a massive thank you to Michael DB and Tom for the effort to create the structure for versatile landings.
And this was the intent, actually. We were adding, Michael at the time was adding in the deep stall, and I was thinking, well, we want physical landings, all these things. I'm like, well, we're going to start hacking out a little bit, so we need to abstract it all out.
Yep.
And so this was a little bit of instigation he was doing, or the inspiration was this and that. So we have a deep stall in there, and the idea is on the helical landing, it'd be the same thing. You just have a land point, and it just figures out the radius. It figures out all these things using the existing parameters that you've tuned for your aircraft. So you just say, the idea is long term to be that land mode. So you just say, switch the mode, and it just comes and lands. And it's the way you want it to be. It's very hard to do on a generic aircraft because the ArduPilot is so versatile for all kinds of things. So it's hard to do that in a generic sense, but that's the plan.
Michael, how about just like if you do the landing and you want to go and flip the whole plane upside down. Let's say if you have an expensive camera payload under the plane, your winglets, just like if you have a delta wing, your winglets are downwards while you're flying. When you're landing, you flip it upside down, so the camera payload and everything expensive is pointing upwards, and you're coming back on your back.
Right. So ArduPilot doesn't support that right now. You could add it. There's an aircraft from AeroVironment, which is military application, but WASP does that already. So that is already an existing thing.
You can actually do it in ArduPilot now because you can have a mission item for fly inverted. And so that will flip to inverted and use to a normal landing mission.
Okay.
So that's actually doable.
I make no promises about what the deep stall controller does if you're inverted.
Philip used it for.
In 2014 for the ABC Spark Fun Challenge, we were originally planning on doing a ball drop by actually inverting the aircraft.
I know we do inversion. I'm just promising nothing about how deep stall navigates when inverted. That's all I'm saying right now.
So the invert bit, like you just continue the mission, like you could just do invert, and then you can continue with a normal land, and it'll land.
Yeah.
What your airframe does, that's up to your airframe design. But
that airframe doesn't like being inverted. We've done it once. I'm good with never again.
Yeah. So deep stall. One thing about deep stall is that once you kind of not flare stall, I guess. Once you trigger the deep stall, you've done your wind estimate beforehand, and you're kind of just gliding into that point. Some things we want to expand a bit is to be a bit more of a fly-by-wire-ish mode. So when you do that, you can actually still navigate and try to hit a spot more precisely, all the way down. You kind of just fly around. So it's sort of like a deep stall flight mode of sorts. So you can deep stall from 100 meters up and just kind of I get right there, and it'll just happen, but it'll happen right at that spot. Buzz, any question?
What about non-aeroplane aircraft? I know we're probably not going to be landing rovers, but what about sub? You know,
All of my rovers are landed. A sub. So how to land a sub?
autonomous.
Just head towards land. Just go north and you'll hit it.
Eventually, we just descend, we'll hit land. Yes.
It's a text system inside sub, and it's got to have a suitable landing approach that the surfaces on the vehicle are capable of handling.
So I wonder. Yeah, I don't know. I'm not sure what landing means in a sub.
Most subs have lifting surfaces.
Right, yeah, I understand, but usually you can just surface and then you're a boat and you kind of go. So landing in a boat is the same thing, essentially.
not all of them. Not all of them are mutually buoyant. So
Yeah,
you have
so-
to have forward. So you're sort of flying.
So you're actually landing on the surface,
You're
eh?
surfacing.
Yeah.
Yeah, and so I understand that concept doesn't apply to copters because I know the sub is more like an underwater copter. So I know that copter we fly over and then go, you fly up and down. The sub can't go over and then go up.
There's
Why
two
not?
types of subs. There's ones that are thrusters, which are probably more like a copter, and then there's ones that are
Effectively
propellant
planes.
back and flaps and
Yeah.
So they're much more like
Well, I was thinking, so in my head I was thinking, if they're coming to shore, you can't just go down underground and go up to the surface. But if you're going to a boat, if it's a boat retrieval, then yeah, you come on you up. But I don't know. Those are questions for the artists and maintainers. I just do planes.
All right. Thank you, Carl.